This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Chapter 4 of the Neural Network Mysteries, Under the Hood of AI. In today's episode, The Secret Sauce, Backpropagation, we're going to unravel the fascinating process that helps neural networks learn from their mistakes. So, whether you're a seasoned techie or just curious about how AI gets smarter, let's dive in. A camera in a hospital spots disease more accurately than most doctors. A camera in a car makes split-second decisions at highway speeds. A ceiling full of cameras at an Amazon Go store watches you grab snacks, then quietly checks you out as you walk away, no cashier in sight. Most of the time, you don't even notice it working. Unlocking your phone with your face, autofocusing on a friend in a crowded photo, blurring the messy background on a video call. These everyday tricks are all quiet victories of computer vision. Behind the scenes, billions of images and videos are flowing through algorithms that have learned, from massive labeled datasets, to spot patterns far too subtle or too fast for humans to track. Deep learning models sift through medical scans, factory assembly lines, traffic intersections, and social media feeds, turning raw pixels into predictions and decisions. Think of it less as cameras getting smarter and more as software learning to see well enough to safely drive, diagnose, inspect, and personalize at global scale. Yet teaching machines to see isn't one thing. It's a stack of specialized skills. One system reads road signs at 120 kilometers per hour. Another spots microscopic anomalies in a retinal scan. Another tracks defects on a conveyor belt thousands of times per minute. Each is trained for a narrow job, tuned to conditions, and evaluated with ruthless statistics, like AlexNet's breakthrough on ImageNet or face recognition surpassing humans on LFW. That's why vision is creeping into everything from crop monitoring drones to stadium analytics, wherever cameras already exist and decisions hinge on what they capture. Walk through a modern city and you're moving through one enormous vision system. Traffic cameras track congestion, warehouse robots follow floor markings, drones survey construction sites, and your doorbell watches the front porch. The common thread isn't just seeing, it's extracting the right signal from endless, messy visuals and plugging it into a workflow that matters. Under the hood, most systems tackle three broad jobs. First, what's in this frame? That's classification, labeling an X-ray as healthy or suspicious, or a satellite tile as forest versus urban. Second, where is it exactly? That's detection and segmentation, putting boxes or outlines around pedestrians, forklifts, tumors, hail-damaged crops. Third, what's changing over time? That's tracking and action recognition, following a specific vehicle across cameras, or recognizing when a factory worker steps into a restricted zone. The magic isn't only in accuracy, it's in context. A model that spots a tiny crack on an airplane wing is useless unless it ties into maintenance schedules, risk thresholds, and regulatory logs. That's why some of the most interesting work now happens at the edges of vision, combining visual cues with sensor data, business rules, and domain knowledge. We're also seeing a quiet architectural shift. Instead of streaming video to distant servers, more analysis runs where the pixels are captured, on phones, cameras, AR headsets, even smart traffic lights. This edge processing cuts delay, preserves privacy, and lets vision power use cases like on-device fitness coaching or real-time quality checks on a factory line with no stable internet. A helpful way to think about this layering is like a financial analyst's workflow. Raw price ticks, pixels, get cleaned and aggregated, basic image processing. Patterns are modeled, vision networks, and then those outputs feed portfolio decisions, applications. Each step adds structure, value, and constraints. Despite headline-grabbing milestones, open-ended understanding remains brittle. Unusual weather, new camera angles, rare medical conditions, or simply a dirty lens can break assumptions. That's why leading teams obsess over diverse data, careful evaluation, and human oversight, not just bigger models. Think of how a good chef uses sight in different ways, checking if a steak is browned enough, spotting a shell fragment in egg whites, or judging whether a sauce has split. Computer vision is playing those same kinds of roles across industries. Highly specific, context-aware, quietly critical. A subtle place you've seen this play out is in modern translation tools. Early systems were filled with handcrafted rules. Today's models mostly rely on large networks trained with backprop, yet what matters in practice is which errors they're pushed to care about. If a translation app is trained mostly on news articles, it may excel at formal language but stumble on slang. The gradients have been tuned to polish one region of language space more than another. The same holds for medical imaging models that focus on certain diseases or code assistants steeped in specific programming languages. Here's where the secret sauce gets practical. The data you choose and how you weight different types of mistakes shapes what the network becomes sensitive to. Penalize false positives more than false negatives, and you sculpt a cautious system. Flip the priorities, and you get something bold but risky. Backprop doesn't decide those values. It faithfully amplifies whatever priorities you encode into the loss and data set. Backprop's future isn't just bigger models, it's smarter corrections. As labs push for lighter training, expect tricks like low-precision math and sparse updates to matter as much as clever architectures. Think of teams tuning a race car. They're no longer rebuilding the engine, they're shaving milliseconds off pit stops. As tools hide more math behind clean APIs, the real leverage shifts to which failures we optimize away, and who gets to decide those priorities. In the end, these microscopic nudges don't just polish models, they shape entire products, from how search ranks results to how filters flag abuse. Your choice of data and loss is like setting house rules for a game. Over time, the players adapt to win on your terms. Your challenge this week: spot one digital system whose rules you'd redesign, and ask how its hidden learner would change. This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!